Hello and welcome to our Superstructures design project for Structures 2 by Samuel Dick,
Olivia Jacobin, Rachel Hockley.
Structures are a part of our everyday life. We encounter them throughout our daily lives, from the roads we commute on, the homes we live in, the businesses we support. They are essentially part of everyday life. Structures are any form of construction that supports loads, resists loads, and transfers loads as shown. The fundamental function of a structure is to satisfy the building's function, resist relative loads, be durable, and minimize the use of resources to satisfy the economical constraints. Industrial buildings come in a range of different portal frame structures, from multi-span to multi-story car parks, all of which present different design problems to be solved. For the given assessment task, an analysis of different loads applied to a domestic shed and how this impacts the design of various structural members and connections, taking into consideration the different load paths of each load. Design of different elements must be in accordance with the applicable industry standards. The given domestic shed will be designed in accordance to AS 1170.0, AS 1170.1, AS 4055, and AS 4100. Domestic sheds have many different structural components, such as columns, beams, footings, and bracings, along with other construction elements, such as roof sheetings, that all must be designed to be able to resist the different loads applied to them. The extent of this assignment will be covering the live imposed loads, dead permanent loads, and to an extent, wind loads, and the impact that these loads have on the design of the structural components of the domestic shed. Design parameters. As Group 41, we had a span of 7 meters, a height of 6.6 meters, wind class N4, design speed of 61 meters per second, column 1 was 3.3 meters, and beam 2 was 3.5 meters. Wind design. We calculate the serviceability limit state and the ultimate limit state with our design parameters in accordance with AS 4055. Here is our wind pressure serviceability limit state and ultimate state, and here is our external wind pressure for shed walls according to serviceability and ultimate, and our shed roof serviceability and ultimate. Middle frame design. The extent of this assignment was to calculate the dead loads on B1 and B2, the live loads on B1 and B2, the dead and live loads for C1, wind loads on the intermediate frame, using the load combinations to find the most adverse combination, and using space gas modeling to compare to our manual calculations. Dead loads on B1 include the ceiling, insulation, service weight, self-weight of the purlin using lyset, same as the roof sheetings, which were also lyset, and the self-weight of the rafter, which was assumed. However, there was no ceiling in our design to maximize the storage space, and here is our total dead load calculation, totaling to 4.87 kilonewtons. Dead loads on B2 include the secondary beam, the self-weight of the rafter, which was assumed, flooring, which we used cement fiber sheets, with our total dead load on B2 equaling 7.62 kilonewtons. Live loads on B1. These were calculated using the Australian and New Zealand standards 1170.1 2002, table 3.2, the reference values of roof actions. The total calculated was less than the minimum, therefore we had to use 1.5 kilonewtons per meter. Live loads on B2. The values of the imposed floor actions, table 3.1 of the Australian and New Zealand standards 1170.1 2002, show for factories, workshops and similar buildings, general industrial, the uniformly distributed actions is 5 kilonewtons per meter squared. Dead loads on C1. To find the dead loads, we must first calculate the tributary area, which is 21 meters squared. Thereafter, we calculate the main rafter, the secondary beams, the flooring elements, the column self-weight. The main rafter and the column self-weight are both assumed in this. Our total dead load was 9.55 kilonewtons per meter. Live loads on C1. This was also taken from the standard, and we used 5 kilonewtons times the tributary area, which gave us a total of 105 kilonewtons. The wind loads on the intermediate frame were calculated through various equations. Here's the external wall wind pressure and suction, the external roof wind pressure, and the external roof wind suction. The critical load combinations were taken from the standard, and this was the most adverse combination. However, we must note that we did not consider earthquake, wind, or snow loads. Earthquake and snow were out of the parameters of this assignment, and wind loads did not affect member B2 or member C1. And that is our bending moment, shear force, and deflection calculations. The critical load combination for C1, we take into consideration the axial forces, with the most adverse combination being the second combination, totaling to 168.96 kilonewtons. Here is our space gas modeling with bending moment, shear force, load combinations, deflection, and axial force. Bending moment and the shear force manual calculations were exactly the same as the space gas modeling, with slight variations between deflection, which would be in the allowable discrepancies. However, our manual load calculations for the axial load had a large disparity between the space gas modeling. The final shed design had to take into consideration the actual amounts of the self-weights for the universal beam and the universal columns that were designed for, and then through trial and error, and then through the design capacity tables, make sure that these are still the best options, and then a serviceability check. The learning outcomes from this assignment shows the methodical process for which portal frame structures are designed, and the many different industry standards that are out there when designing portal frame structures. Thank you for listening.